In today's lesson, we will develop the sufficient condition for the equilibrium of the rigid body. In contrast to the forces on a particle, the forces on a rigid body are not usually concurrent and may cause rotation of the body due to the moments created by the forces. For a rigid body to be in equilibrium, the net force as well as the net moment about any arbitrary point O must be equal to zero. In this way, the body can neither translate nor it can rotate. First, we will consider a case where the force acting on a rigid body lies in a single plane. This type of force and couple system is often referred to as two-dimensional or coplanar force system. For example, the airplane shown here has a plane of symmetry through its center axis, and so the load acting on the airplane are symmetrical with respect to this plane. Thus, each of the two wing tires will support the same load T, which is represented on the side view of the plane as 2T. For analyzing actual physical system, first we need to create an idealized model. Then we need to draw a free body diagram showing all the external forces. Finally, we need to apply the equation of equilibrium to solve for any unknowns. But before presenting a formal procedure is how to draw a free body diagram, we will first consider the various types of reactions that occurs at supports and points of contact between bodies subjected to coplanar force system. If a support prevents the translation of a body in a given direction, then a reactive force is developed in the opposite direction at that point. If a rotation is prevented in a given direction, then a reactive couple moment is exerted in the opposite direction. For example, let us consider three ways in which a horizontal member, such as a beam, is supported at its end. One method consists of a roller or cylinder, since this support only prevents the beam from translating in the vertical direction. The roller will only exert a force in the beam in this direction. The beam can be supported in a more restrictive manner by using a pin. Here the pin can prevent translation of the beam in any direction, and so the pin must exert a force on the beam in these directions. For the purpose of analysis, it is generally easier to represent this resultant force by its two rectangular components. The most restrictive way to support the beam would be to use a fixed support. This support will prevent both translation and rotation of the beam. To do this, a force and couple moments must be developed in the beam at its point of connection. Here is the list of some common types of support for bodies subjected to coplanar force systems. In all cases, the angle is assumed to be known and the surface is taken as frictionless. In cable type of connection, there is always one unknown. The reaction is a tension force which acts away from the member in the direction of the cable. The weightless link connection also has one unknown. The reaction is a force which acts along the axis of the link. Similarly, a roller in confined smooth slot, rocker, smooth contacting surface, member pin connected to a collar and smooth rod, all these cases prevents motion in one direction. In smooth pin or hinge, there are two unknowns. The reactions are two components of force, or the magnitude and direction of the resultant force. In a member fixed connected to a collar on smooth rod, there are two unknowns. The reaction are the couple moments and the force which acts perpendicular to the rod. Finally, in a fixed support, there are two unknowns. The reaction are the couple moment and the two force components. It may be noticed that the internal forces that act between adjacent particles in a body always occur in collinear pairs, such that they have the same magnitude and act in the opposite direction. Since these forces cancel each other, they will not create an external effect on the body. It is for this reason that the internal forces should not be included on the free body diagram if the entire body is to be considered. Engineers sometimes consider a proper idealized model that gives an approximate result to the actual situation. Let's study a case to develop one such model. A steel beam is to be used to support the three roof joints of a building. For a given analysis, it is reasonable to assume the material is rigid since only very small deflection will occur when the beam is loaded. A bolted connection at A will allow for any slight rotation that occurs here when the load is applied, and so a pin can be considered for this support. At B, a roller can be considered since this support offers no resistance to horizontal movement. Finally, the weight of the beam is generally neglected when it is small compared to the load the beam supports. The idealized model of the beam is therefore shown with average dimensions A, B, C, and D. In this case, consider the left boom. It is supported by a pin at A and by the hydraulic cylinder BC, which can be approximated as a weightless link. The material can be assumed rigid, and with its density known, the weight of the boom and the location of its center of gravity G are determined. When a designed loading P is specified, the idealized model can be used for a force analysis. Consider this example in which the operator applies a vertical force to the pedal so that the spring is stretched 1.5 inch and the force in the short link at B is 20 pounds. An idealized model and free body diagram of the foot pedal are shown here. Thanks for watching.